between. Pamela, did you study in the morning or not?
ค่ะ
Did you come in the class this morning?
sorry ค่ะอาจารย์
Becauseอาจารย์นิคม talk to me, Pamela is absent. Fluency or not? I have no answer for อาจารย์นิคม Okay,
ค่ะอาจารย์
continue our class.
ค่ะ
Okay, we'll continue our class.
โอเคค่ะ
Forgot it. Okay. Okay, this is the main component with to optimize it. It's the same previously. That's like what is your objective? Our objective we would to maximize, we would to minimize, or sometimes we would like to get the target value that we would like to get that previously. That's right. As I use the minitab, we have the maximize, minimize, and also some target. You would like to find the condition that gives your target. Right. Okay, the first you have to the function or equation. What is the function that we would like to optimize, maximize, minimize, or target? And also we have some condition. The condition we call this is subject to. We have some condition. It may be function is less than or equal to beta 1. We have some limitation of your function. If you would like to find the optimum condition for temperature, and also sometimes you have some limitation. The temperature should be between 10 and 20. For example, this is we call the constraint or subject to. This is the constraint. Okay, we have the function for objective and constraint or subject to for this. Okay, for this we talk about the linear programming. That means all functions should be linear. If we talk about the nonlinear programming, a function is maybe linear and also mixed with nonlinear. That's right. I think you know about the linear. It's maybe a plus b x1 plus c x2 plus b x3, for example, this linear. If you have a equal to y equal to a plus b x1 x2 plus b x3 square, something like this. This is non-linear. Okay, but for this case, we call it linear. It's linear. Okay, for example, we have the objective function is c1 x1 plus c2 x2 plus cn xn, and also we have the decision variable is x1 x2 xn for this, and it's maybe we have some constraint or subject to. Right? This is quite complex. As I talked to you on integration in linear integration, and we have only one equation, but this we have some constraint. As constraint is also complex. Constraint is a function also. Right, in function also. A11, x1, A12, x2 is maybe less than or equal to some constant, greater than equal to some constant. This is the constraint. Right? This is a constraint or sometimes we call subject to. Right? The maximum and decision variable should be correlate with this subject or this is constraint for this. Okay. For this case, we would like to give you some example. Screw is hot tube manufacturer. การกด recording not yet. Okay, sorry. record ละ Okay, record ไว้ไหนเนาะเนี่ย I record in the cloud in this computer. Cloud. I forgot. เมื่อกี้ฉันกด in the cloud or in this computer. ไม่จำเลยไม่ได้ใช่ไหมถ้าในคอมพิวเตอร์จะต้องกลับมาโหลดแต่คอมพิวเตอร์นี้ Okay. Okay, look at this. The manufacturer would like to produce a hot tube, right? And we have two models for this hot tube. We call aqueous bar and hydraulic. We have two types of this. John, the owner and manager of the company, need to decide how many each type of hot tube to produce. That's right, during his production cycle. Okay, for this, he buy fabricatable fiberglass hot tube shell from local supplier at the pump and tubing to the shell and create his hot tube. Okay, but for this supplier, that's right. For this supplier, have some capacity to deliver or to transport the hot fuel. We thought, okay, he installed the same type of pump into what hot fuel. He will have only 200 pump available during the production cycle. Okay, from the manufacturing, the main difference between the two models of the hot fuel. Okay, again, they have to produce a plasma model and hydroxide. This difference is for the plasma require 9 hours for labor, 12 feet of tubing. This is for plasma. And hydroxide requires 6 hours and 16 feet of tubing. If you produce a plasma model or hydroxide, plasma, okay, we need at least 9 hours for laborers and 12 feet of tubing with the length of the tube. Okay. And also, the John or Hobby expected that 1,566 production labor hours aside and 2,880 feet of tubing available. We have this available in your plan for the production. And the profit for each, like for each, the $350 for a cost plant and $300 for hydro. Okay, after you produce each of the apostrophe, you will get the price, the profit from the apostrophe is 350. That's after you sell it, you get the profit. That's right. For apostrophe 350, hydro 300. If you consider for some approximate, we can find that a cost per will give the better price. But a cost per needs more than working hour for labor. It may be some cost for this. You have to compare how many products you produce from a cost per model, how many products you produce from hydraulic model. That gives the maximum your profit. For this case, we would like to maximum your profit. And also we have some limit. Like for the total labor hour for two of it, we have 1,566. This is the limitation hour. And also the tubing length, we have 2,080, 880 feet for this. This is the limitation. Okay, the question: how many apostrophes and hydraulic should produce if you want to maximize the profit? That's right. If you would like to get the maximum profit, ต้องการได้กำไรสุด That's right. How many apostrophes? How many hydro? Okay. Okay, and then you summarize. For this case, we have the apostrophe hydro. One pump, we need one pump. That's right. For this, we have the pump for each model. Okay, apostrophe, okay, we need one pump. Hydro, we need one pump. And labors, for apostrophe, we need 9 hours. And for hydraulic, we need 6 hours. The length of the tube, apostrophe is 12 feet, hydraulic is 16 feet. The profit from apostrophe is 350, hydraulic is 300. But we have some limitation of this. We have only 200 pumps. That's right. We have only 200 pumps. And 1,566 hours. And 2,880 feet. This is the limitation. That's right, the limitation. Okay, now we understand the problem, right? What if we would like to design? We have, okay, X1 is number of phosphate to produce, right? X2 means number of hydrogen to produce. The objective function, we would like to optimize the profit, that's right, without of the profit. X1, number of the phosphate, and you know the profit from phosphate is 350. This may be X1 multiplied 350. Because $350 is $350 per one cost part, right? X1 is number, X2 is number of dollar, multiply $300 per piece of the hydrogen. This is the maximum condition. That's right. We would like to maximize this profit because 350 is the price of the cost part per one piece. X1 means number of cost part. Okay, and this is the objective. We would like to maximize this, to maximize profit. Yeah. The constraint, the pump, we have the maximum pump or the limit pump is only 200 pump. That's right, 200 pump. This is the minimum. That means X1 multiply 1 because for each piece of the product, we need only one pump. That's right. One pump multiply X1 plus one pump multiply X2. This is the number of pumps we use. That's right, the pump we use. It should be less than or equal to 200 because it's only maximum 200. The second condition, the labor time. That's right. The labor time we have the limit at 1,666. That's right. If you produce a cost by X1, 9 hours for cost by. That's right. 9 multiply X1. For hydraulic 6 hours multiply X1. And totally should be equal or less than 1,566. It is the second condition. And the third condition, tubing length. That's right, tubing length. For a crossbar, we need 12 feet, and hydraulic we need 16. But we have the limit at 880, or we should be equal or less than. We have to optimize based on this constraint or condition. Based on this constraint or condition. Okay. And then we have X1 and X2 for another constraint. X1 should be equal or greater than 0. That's right. Number should be greater than or equal to 0. We start from 0. 0 means you do not produce this. That's right. X2 also is greater than or equal to 0. This is some upper or lower bound. That's right. It also constraint. We have 1, 2, 3, 4, 5 constraints. That's right. 5 constraints. Okay, summarize this. We have the objective, subject to or constraint. We have 5 questions for constraint. We would like to optimize this based on 5 conditions. Based on 5 conditions. We would like to solve for X1 and X2. X1 means number of a crossbar that you would like to produce. X2 is number of hydraulic you would like to produce. That's right. For this case, we have many techniques. That's right. For the first one, the constraint. Okay. For idea is a cost by X1 because a cost by X generate the higher price or higher profit. Okay, that means sometimes if we assume X2 equal to 0, right? X2 equal to 0. That means the first constraint, second constraint, the third constraint should be X1 should be less than or equal to 174. Right? If you produce also X1, you will produce only 174. Right? If you calculate based on the third constraint, X1 should be less than 240. The third is not possible. That's right, not possible. Because the limit is only 200. That's right, 200. We have 200 pump. It depends on pump also. Depends on pump also. And we do like it, we will get the profit is $60,000. At the top level, it's not possible because X1 is maybe less or greater than like 200 or something like it. Okay, we will use the linear programming technique. Linear programming technique. For this case, we have 2 variables, X1 and X2. I will show you 2 techniques by graphical and by Excel. By graphical, you have to identify the physical region. Right, that is the optimum solution can be found in the feasible region. Okay, look at the graphical curve. We have x1 and x2, right? We have x1 and x2, and then you plot the first constraint, right? The first constraint we start from x1 plus x2 equal to 200. This is linear. That's right. It's easy because it's linear. If you substitute x1 equal to 0, you get x2 equal to 200. This is this point. That's right. And then if you substitute x2 equal to 0, you get this point. Okay, this is the first. This is the feasible region for this. Okay, for the next, you put the second constraint. Right? The second constraint. This is the time, right? Based on labor hour. If you substitute x1 equal to 0, you get this point, and you get this point. Sorry, this point. Okay. From this, we have this, and then we have this the collapse area. This is the collapse area between two lines, right? Between two lines. Okay. This is the collapse area. This is the feasible region. Right? Okay. Because these two lines contact at this point. Okay. This is the feasible region. And then you add the third equation, the third constraint. Sorry, the third constraint is at x1 equal to 0, we get this line. That's how we get this, and then we get this. Okay, this is the collapse area of these three equations. These three equations, like this. Okay, and then we add for this. I think we have the objective function because we have the area for possible area like this area. And then this is the equation for objective function, right? Objective function. Okay, if you substitute in this point and this point, you get this line. And also you can vary x1, x2 for this. At 0, x1, at 0, x2, you get this line. And then you vary again at this point. Right, you get this point. Okay. You found that this is the maximum, right? From previously we have this one, but we don't know this maximum or not, right? And then you follow the objective equation, move until it's contact with this, right? Contact with this, right? Okay, if you do by graphical technique, you get the maximum point at this, right? The maximum point at this point. What is x1? What is x2 at this point? And then you get the maximum. x2, x1, right? You substitute x2, x1 into this equation, you get the maximum. Right? You get the maximum. Right? Optimum condition. Okay. Okay. Right. This is the optimum. This is at 66,000. That's right, $66,000. At the x1, you have to produce x1 is 122. x2 is 78. That's right. You cannot produce only x1 because x1 is higher profit, but the optimum is not. That's right. You have to mix between x1 and x2. For this case, we have only one optimized, like one optimized point. But sometimes it's more than one point. You can do that. That's right for that. Okay, this is by graphical technique. Like graphical technique. Okay. And also we can find that this point, like we show the profit like this, 54, 64, 66, 60. That is it. Okay, that's correct. This is the maximum. That's right. You will produce the maximum profit by using 122 of phosphan and 78 of hydrogen. And then you will get the maximum profit based on condition, right? Based on 200 pump, based on the 900 for 9 hours for phosphan, 6 hours for hydrogen, for example, and limitation of the tuning, and then you get the optimum condition like this. Okay, this is based on graphical technique, right? Based on graphical technique. Okay, this summarize some the technique for graphical technique as I show you previously. Right, the first step you plot the boundary line or the constraint in the side, and then you collect the area that all of the line connect, all the line connect. That means that we talk about identify the visible region, right? And then you locate the optimal solution by plotting level curve based on the optimum objective function, that's right, objective function. Okay. But for some time, we have at least 4 feasible alternative optimal solution, redundant constraint, unbound solution, and infeasible. I will show you for the first one. Right. For this case, we have some alternative optimal condition. This is the same optimum but different condition. You can produce to get the maximum profit at 70,000, 78,000, right? 78,000, but not only one condition. That's right. We can produce to get the maximum at any point because the line is compared like this, not only one point. This point is only the maximum. That's right. The same profit for this. This is we call the alternative optimum solution. That's right. We can produce at the maximum for this. And for this case, we call the feasible region, right? The feasible region. But for this case, we have some this line. This line is not collapse with each other. This line is collapse with each other. And this is we call the unbound solution. We cannot find the solution in this. Because the feasible region is in this zone. For this case, we cannot find the solution. That's right. And the last one, because this is the infeasibility. That's right, infeasibility. No collapse for instance. For this case, we cannot find the maximum, minimum, or target. This is we show you based on the graphical technique, but graphical technique is quite time consuming, for example. But now we can apply the program. You can use the Minitab or you can use the Excel. For this case, we use the linear program in spreadsheet or Excel. Okay, we look at the example, the previous example. Okay. For this case, this is the summarize your objective maximum. That's right. And we have the constraint, we have 5 constraints. The pump, levels, tubing, and non-negativity or the constraint for x1 and x2, not negative, right? That's right. The number should be 0 or positive, right? Okay. And then we have to set up the target cell in Excel or software with our objective function or target cell. And changing cell that means the decision variable if you found in Excel. And constraint, assign this constraint or subject to for this case. Okay, I will show in Excel. Okay, if we this is number, right? Number of the product that we would like to produce. We have 2 models at the cost by a Q UA Q A and hydro that VRO. Okay. For this case, we would like to produce number maybe from 0. The minimum is 0. Okay, we can choose the minimum at the initial gate, for example. Okay, we assume 0 for initial gas and unit profit per each just like unit profit. Okay. Unit profit for a cost by 350. And for hydro is 300. And the total profit is equal to x1 multiplied 350 plus x2 multiplied 300. X means number of alpha 1, that's right. X2 means number of hydro. Okay, for this case, x multiplied 350 plus x2 multiplied 300. Okay, this is the total profit. Now it's 0 because we produce 0 x1.
Ajahn, we can see the Excel
Okay.
in Zoom.
Okay, for this case, thank you for that. Okay, for this case, we look at this. Okay, for this is the x1, x2, right? This is the profit per piece of alcohol and per piece of hydro. And target, this is come from x1 multiplied 350 plus x2 multiplied 300. Okay, this is our profit. That's right, our profit. And then we try the constraint. We have 5 constraints aside, but a function of only 3 functions. Constraint. We have the pump constraint. This it should be unit aside in unit. The second one is labor constraint in hour per unit. And tubing or the length of tubing. Is it the feet per unit? FET per unit. Okay. Okay, the pump. We need 1 pump for phosphor, 1 pump for hydro. That's right. And 9 hours for phosphor and 6 hours for hydro. Tubing length is 12 feet for alcohol and 16 feet for hydro. Okay. When you now use QSE, we use this. It should be okay. We use pump 1 pump per 1 phosphor. That's right. That means x1. You have to check. This is the x1 multiply 1 plus x2 multiply 2. That 1 means pump for alcohol and 1 pump for hydro. Yes. Equal to x1 multiply this side. And this is for hydro multiply. This is for pump, and then for labor, that's right, equal to x1 multiply 9 hours for x1, that's right, plus x2 multiply 6 hours for x2, like this. This also x1 multiply 12 plus x2 multiply 16. Okay. This is that we use, but now we use only 0, we get 0. Okay, and this is the available, this is the maximum limit. While for pump we have only 200 pump, and pump have only 1,566, and the tubing we have only 2,880. This is the limitation. That's right, limitation. Okay, and then we optimize this. For this is I show you a lot for the Excel solver. That's right, the objective. For this case, you would like to maximize. That's right, and the same in cell. And also you add some constraint. That's right, you add some constraint. You have 3 constraint. This is constraint. Okay, what constraint? Copy. Okay, for this we go to data. Right? Solver. Okay. Objective. The objective is total profit. That's right. You would like to maximize the total profit. Okay. Our objective is this. Cell D4. Okay, we select cell D4. We would like to maximize, minimize, or set target. This set value of that is the target. As a particular case, we use the maximize. The cell that we decision or shrinking V3, C3. You would like to establish number of accord and number of hydro. That's right. Number of accord and number of hydro. Okay, we choose. Okay, 2 of this. Right, 2 of this. And then we have constraint. We have to add a constraint. We have constraint is V3 greater than or equal to 0. X1 and X2 is greater than or equal to 0, right? The first 2 constants, X1 greater than 0 or equal to 0. X2 greater than or equal to 0. Okay, the first constant we choose this, right? These 2 parameters, X1 and X2. And then for this case, we can choose less or equal to, greater than or equal to. For this case, we choose less than or equal to, or not greater than or equal to, greater than or equal to 0. Okay, right, so, okay, so you click, we add this already, the first one. And then, the next one, we have some constraint for this, this constraint. Less than or equal to 200, less than or equal to 163. Right. Okay, we shoot these 3 equations. That's right. These 3 equations should be less than or equal to this variable. That's right. We can choose 3 of them. That's right. We can choose 3 of this. This should be less than 200, less than or equal to 100. This should be less than or equal to 1,500. Yes, it should be 3. Okay. Okay. Then this 5 condition, that's right, x1 greater than 0 or equal to 0, x2 greater or equal to 0, and then term of this. Okay. If you would like to analyze, for this case, we have the linear. We use the simplex linear programming. That's right, with non-linear. This non-linear. Okay, we have simplex linear programming. That's right, this is a linear programming. And also, sometimes we would like to take your answer sensitivity. Okay, we can click okay. Right. And then you get your answer. Right. Quickly. This is you have to produce 122 alpha, 778 alpha hydro, and the profit is 66,000 baht or $66,000. That's right. And we use pump 200, okay, or pump what use. And the labor we use all of the time available. But the shipping we only 2,700. Right, it's about 288. The size is not used, for example, because not excellent. It's about 80. Okay, that's right. It's about 100. A little bit. Okay, this is your answer. Right. And also you can show about the answer or sensitivity limit for that. This is the technique by linear programming. You can try to do this before you get the answer condition. Right. Finally, you get the profit is $66,100. That's right. When you produce 122 alpha 78 hydro. Right. And time that you use is 200. Time and labor required. You use all of this. That's right. Number of time labor required. But the length we only use 2,712. That's right. 212. It's on the tubing limit in your company. This is also we can analyze this. And for another, we use this model. We have model 1, 2, 3, and also we have the M1 and 2, M3 number of model 1. B is number of model 2 solid for the safety different. And also the maximize is quite complex for this. We have 3 models. And the number and number of model we have 6 parameters. Previously we have only 3 parameters. But now we have 6 parameters. This is objective. And also we have the constraint. We have constraint based on resource constraint, based on demand constraint, based on non-negativity condition. Negativity is not mean assign. It should be 0 or greater than 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 conditions. 11 conditions. And also you can contract the spreadsheet. Okay, we have the number that you would like to produce, model 1, model 2, model 3. We will make or we will buy. We combine the making by your company and with the by formator company. How many model 1 you will make by yourself? How many model 1 you buy from another company? And then mix of this and then you find the optimum need to buy together. This cost, total cost should be okay. For this case, we would like to minimize, not maximize, because we would like to collect the cost. Cost should be minimized, profit should be maximized. ต้นทุนคนต่ำที่สุดกำไรมันสูงที่สุด This is the cost should be minimized. And we have some the demand constraint and also non-negativity. That's right. Okay, this is the spreadsheet. The constraint, the winding hour per unit we have for this model used and viable. We have some limitation. 10,000 this is viable or maximum. 5,000 for viable. Viable demand for this. Okay. Cost. That's right. Cost that you do by yourself and cost that you buy from another company. And then we calculate total cost. How to calculate total cost from this? This is the total cost. Right? Okay. This is only we fit the model already. This is the final solution. I would like you try to use the Excel for test this. Right. And another example, this is we blending some at-risk for each company to sell agricultural product to farmer. Right. Okay, we would like to pass on the feed mixing and the feed for animal. Usually we need the feed for animal. ก็คืออาหารสัตว์นะครับ We have 4 types feed. Feed 1, feed 2, feed 3, feed 4. Each feed may have component of corn, grain, mineral. We have 3 of these components mixed together for the feed. Again, feed is the food for the animal, right? The food for animal. Okay, this is the feed 1, feed 2, feed 3, feed 4. Any different composition of the material. Different composition of corn, grain, and mineral. And also, each feed we have some cost per pound of the product. Here we have some constraint. This company received an order from local chicken farmer, 8,000 pounds of feed. This is the order from local, 8,000 pounds of feed. The farmer wants this feed to contain at least 20% corn, 15 grain, 15 mineral. What should I go to fulfill this order? At minimum cost. We would like to produce this follow the order of the customer, and also we would like to minimize the cost together with this process. Okay, the number is the X1 is our mass of feed 1 used in the mix. X2 is the mass of feed 2, X3 mass of feed 3, X4 mass of feed 4. This is the composition or percent of feed. That's right, X1, X2, X3, X4. We would like to minimize the cost. That's right, minimize the cost. Because we know the cost per feed, right? 0.25 feed 1, 0.3 feed 2, 0.32 feed 3, 0.15 feed 4. You would like to minimize this cost? Okay. Because X1, X2, X3 is the feed, mass of the feed 1, 2, 3, 4. And then you modify this, you get the objective function. Right? This is our objective function. And also our constraint, because the power of the feed is maximum is 8,000. That means F1, X2, X3, F4 should be maximum is 8,000. Right? 8,000. And 20% corn, that's right, 20% corn. We have the 0.3, 0.5, 0.2, 0.1, and divided by the power of the feed, or mass of the feed total. This should be greater than or equal to 0.2, right? 0.2. That means you have to add corn at least 20%. Right? At least 15 grain. Right? It is 15 grain for this. At least mean minimum. That's right. I wouldn't go to you. Now that's what okay. And this is the at least mineral. Like for each component, we have the minimum 4% grain and percent minerals. That's right. Okay, and also X1, X2, X3, X4, it should be negative. It should not be negative or non-negative. That's right. It should be 0 or greater than 0. For this. And also the same, you construct the spreadsheet. We have the number of pound for each feed. That's right. And unit cost, cost per each unit, and percent of grain for mineral for this case, and remain and total cost. Now, I think, this is okay. I would like you try to take yourself for the last two examples. I show you the first example. This is we use the solver that based on linear programming, but I think non-linear programming you choose the same. That's right. When you Excel, you choose the non-linear side for the scale because sometimes the objective function is maybe 50m1 square, 50m1 m2. This is non-linear. That's right. This is non-linear. And also when we add the data in Excel, it's the same thing. The constraint is maybe 2m1 plus 1.5m1 square. This is non-linear. You could do the same technique, but the equation is non-linear. That's right. Equation is non-linear. Okay. เอาแค่นี้ดีกว่าน้องมองแล้วแต่มันหมดสไลด์แล้ว Sorry. Okay, this is the all of the topic that we talk to you in data analysis and experimental design. Okay, this is the topic I will talk to in this term. And also the next topic for material engineering, we will talk about the AI basic with Ajahn Wood, like 3 weeks. And also, I think Ajahn Wood will also assignment, no exam. But previously is no exam. Right? Only my section will be exam. And also after the Ajahn Wood, and then we would like to do presentation of the paper. That's right. Presentation of the paper 10% or 15%. That's right. And also for the paper, I will assign you in the classroom. You have to find at least 2 papers related only 2 papers, not actually, only 2 papers that related to your research or related topic for you that apply about the ANOVA analysis, about the experimental design, design surface methodology, something like this. I will write this in the Google Classroom and submit me, and then I will shoot one for your presentation. One for your presentation. Okay, the date of presentation it should be after Ajahn Wood for material engineering and chemical and talk to you about this. If you have any question for paper, I will assign you in Google Classroom again. That's right. And then you submit in Google Classroom, and then I will shoot at least one for your presentation. For material engineering, for Ajahn Wood, Ajahn Vimona will also attend, like in the presentation class. Okay. For the next, how about the Excel? Right. Okay, for my class, my section, I will separate